Welcome back. It is time to finish off Chapter 12 of Pre-Calculus Made Difficult. And today we will be discussing transformed sine waves, which are involved in many of the most important applications of trigonometry. But I think it's worth taking a moment right at the beginning to reflect on how far we have come in our understanding of the sine function. We first met sine and its trigonometric fellows in the context of right triangles. It was in that setting where we met the great god 𝑘𝑒𝑎𝑙𝑙𝑢𝑠. But from there, we generalized the definitions of the trig functions, and the geometric figure on which we became most fixated was the unit circle. But as we moved from triangles to circles, expanding the domain of the sine function dramatically, we were led to consider the remarkable graph of the sine function, which takes the form of a wave. And at this stage, trigonometry begins to become applicable to things that, at least on their surface, have nothing to do with triangles, circles, or rotations. Waves are all around us, not just in literal water waves, but in light waves and sound waves, and even stranger things that you can study if you go far enough in physics. But the waves in which we are ultimately interested are rarely as simple as the bare, unadorned sine wave. Instead, what we are usually interested in are the kinds of waves we get if we start with the sine wave, transform it in various ways, and then combine several, often very many, different transformed sine waves into one. In this video and the corresponding section in the book, we are going to talk about the transforming side of it, but not so much the combining side of it, which requires more advanced mathematics. But to give you a sense of what I'm talking about, I want to show you an example of the result of lots of transformation and combination of sine waves. Specifically, I want to show you one particular sound wave. So, you are now looking at the first movement of Bach's masterpiece, The Musical Offering. Not the sheet music, but the actual waveform from a specific performance. And it might not look terribly wavy to you at this point, but let me zoom in a bit on it. And as I do so, you can begin to see what initially looks like a solid mass resolving itself into a wave. Now, we have zoomed pretty deeply into this. Everything you are seeing on the screen right now takes place within a 50th of a second. But within that 50th of a second, this shows the sound wave that is leaving the chamber orchestra that is performing this and reaching your ear. And I will show you in a moment on another program how we can build up graphs that look like this sound wave. We're not going to get that one exactly, of course. But for now, let's zoom back out so that we can see the entire waveform. And just for a moment, let's listen. I could listen to that all day, but the trigonometric show must go on. And now I am jumping over to the graphing program Desmos to show you how we can take a sine wave, perform some simple transformations on it, and then combine those transformed versions to get something that at least begins to resemble that waveform we just looked at in Bach's Musical Offering. Oh, but before I do that, note that the function I have entered on the left side of the screen, f of x equals sine x, there's no theta in sight. I'm just calling the input variable x. That's fine, of course. The input variable is just a so-called dummy variable. If we were talking about the squaring function, in other words, the function that turns 8 into 64 and minus 9 into 81, it doesn't matter whether you call it x squared or z squared or theta squared or q squared or whatever. Same story here. The function itself is the thing. We can call it sine of x or sine of t just as easily as sine of theta. We used theta as we developed it for its association specifically with angles, but we can use any input variable we like. Anyway, there is our familiar basic sine wave with a period of 2 pi crossing the horizontal axis at every multiple of pi. But for our first version of a transformed sine wave, let's try not sine of x, but sine of 2x. You might take a minute and see if you can guess what the graph is going to look like. If you've been reading the book straight through and you've already read chapter 6, you should know exactly what the graph is going to look like, because all we've done here is substituted 2x for x. And that kind of algebraic transformation corresponds to a specific geometric transformation. I'll describe this in more detail when I'm back on the blackboard, but for now, let's see what it looks like, which is this. Still looks like a basic sine wave, but it's compressed. It has been smushed horizontally. One full wavelength is only half as long as what it was before. This new function, sine of 2x, has a period of pi. That's the basic pattern that repeats itself over and over again, rather than 2 pi for the original function. As I say, we will discuss this in more detail very soon. What I want to show you, though, is we've got the original sine wave and now a transformed version of it. And if I now add those two together, in other words, if I take a third function, which I will call h of x, which is sine of x plus sine of 2x, what will the graph of that combination of these two functions look like? That sum of those functions. This is a little harder to guess, but you might see a few things right away. For example, to get the output of this function, you add the outputs of the two previous functions. So when x is 0, both of the component functions had an output of 0, so the output of h is going to be 0 as well. That means when I show you the graph, it's going to pass through the origin as well. And we would have to make such considerations at every possible input. Well, let's go ahead and see what it looks like right now. Aha! This new function does pass through the origin as we said it would, and you can see that it has some very high peaks going above 1 where the sums of the two original outputs exceeds 1. And similarly, it has some lower troughs below -1 for the same sort of reason. Let's knock out the first two graphs and just look at that one. Well, I hope you can see that just by adding two sine waves, the original plus a transformed one, we already start to get something that begins to look like that sound wave we were considering a moment ago. And we can add more and more terms on this, like this, where I've added on one more term, sine of 0.1x, or we could add in another like cosine of 8x, which alters it again. As I said, the combination of the terms is not something we're going to be following in this class because it gets very strange very quickly. In fact, we usually end up considering infinitely many terms all at once. How do you do that? Well, that's a good ways in your future. That would take us into Fourier analysis, which requires quite a bit of calculus as a prerequisite. But it's something to look forward to in your future. And for now, I hope I've made the point that these transformed sine waves, and yes, I know I threw a cosine in there, but cosine itself is a transformed sine wave, that these transformed sine waves are important. So let me jump back to the blackboard. I feel like I'm back home. Well, to understand what comes next, we are going to need to review some basic coordinate geometry from chapter 6 in Pre-Calculus Made Difficult. So let's begin by supposing that we have the graph of some function f, or in other words, our graph is the graph of the equation y equals f of x. So this can't be any old equation. It has to be one in this particular form, where we have y isolated on the left-hand side of the equation, and the right-hand side is just a function of x. There are no y's over here. Okay, suppose we have such a function and its graph. Now, suppose I want to consider the graph of y equals 2 times f of x. What would the graph of that thing look like? Well, this is very simple. Well, look, how do I get points on that graph? For any value of x we take, first we find the value of f of x, which we would read off of the graph, and then we would simply double that value, and that would be a point graph of this new equation. So for instance, if we pop x equals 0 into this equation, well, f of 0 is -2, but we don't just want the -2, we want to double it, which would give us this point at -4. Similarly here, where the original graph crosses the x-axis, whatever that value of x is, f of x is 0 there. Well, if you double 0, you still get 0. So that point is also also on the new graph. And one more, whatever this value of x is. When we stick it into f, we get 4. But if I double that 4, it shoots it up to 8. And of course, this is going to happen with every point on the graph. The y coordinates are all going to be doubled. So the net result is that our original graph gets stretched out vertically by a factor of 2. So this is the graph of y equals 2 times f of x. And it's fairly obvious, having seen this one example, what would happen if we use some other factor other than 2. Like if we wanted to look at y equals 3 times f of x. Well, of course, that would just take all the points on our original graph, keep their x coordinates, but triple their y coordinates. So we would end up with this graph. It's the original graph stretched vertically by a factor of 3. Okay, I think you see what's going on here. If we start with an equation of the form y equals f of x, and we transform it by doing something algebraically to it, if we multiply the right-hand side, that's what my RHS stands for, if we multiply the right-hand side of an equation of this special form by some constant k, if we make that algebraic move, turning this equation into this equation, what happens geometrically? I'll write that on the top of my wiggly arrow. Well, what happens geometrically is we get a vertical stretch of the graph by a factor of k. So when k is 2, we stretch this thing vertically by a factor of 2. K is 3, we stretch it vertically by a factor of 3. Very simple. But there are two little observations I want to make. First, in the examples I gave here, our k, our stretch factor, was greater than 1. But what if it hadn't been? What if it had been a number between 0 and 1, like a half? What would that do geometrically to the original graph? Well, I think you can see that without too much trouble. You take a value of x, let f have its way with it, and then cut that value in half. So instead of sending the point up here, it would send it down here. Instead of sending this point up here, it would send it down here. Instead of sending this point down here, it would send it only halfway down there. So of course, the graph is just going to be smushed, compressed. Not hard to understand. But I just want to point out that when I say stretch by a factor of k, maybe I should put scare quotes on stretch, because sometimes the stretch is really a compression. It's really more of a smush than a stretch. But that's fine. We're using stretch in a more generalized sense. We would still say this thing has been stretched vertically by a factor of 1/2. And you would know that means smushing it 1/2 of what it was before. Okay, so that's the first of the two little things I wanted to point out. The second is this. What if k, the factor by which I'm multiplying the right-hand side in that algebraic transformation, what if k is a negative number? Then what happens geometrically? Like what if I looked at y equals negative f of x? So I'm multiplying by -1. My k factor here is -1. What would the graph of that look like compared to my original white graph, y equals f of x? Well, for every x, evaluate f, which takes us up to the white graph. We get a certain y coordinate, but then I'm told we have to negate that. So I don't want, like in this case, the value of 3. I would actually want -3. So I'd get a point down here, or here, where I put a x value in, and I get a 4. Well, I still have to negate that. So that would give me a point whose y coordinate is -4. Or over here, when x is 0, f of x is -2. Now I still have to negate that. So that -2 would flip up to +2. And no matter where I do this, I'm always getting a reflection. And in fact, the overall graph will be a literal reflection of the original one across the horizontal axis. So when k is negative, I get a reflection, as well as a stretch if k is not -1, but minus something else. Like if I was looking at y equals -2 times f of x, well, of course, I'm taking all the points on my original, doubling them, and then reflecting. So I would end up with something like this orange graph of y equals -2 times f of x, which took the original, stretched it by a factor of 2, and reflected it over the horizontal axis. Okay, well, I think you've definitely got the point now, and we've considered all possible cases. Well, I guess strictly speaking, we haven't considered the case of y equals 0 times f of x, but of course, that would just be y equals 0, which everybody knows is a flat line. All right, now we really have been exhaustive. And that is going to lead me to make one tiny change in the geometric description of what happens when I make this algebraic transformation. Algebraically, when I multiply the right-hand side of an equation of this form by k, I get a vertical stretch by a factor of k, but I have to add a little note with a vertical reflection if k is negative. And when I say vertical reflection, I just mean the points themselves are going to be moving vertically. They are being reflected over the horizontal axis, but they themselves are moving vertically. Just like a vertical stretch means the points are moving vertically. Okay, so that really tells you everything that can happen when you start with y equals f of x and multiply the right-hand side by k. This algebraic move corresponds to this geometric transformation. A vertical stretch, possibly accompanied by a reflection if k was negative. Now, there's another very simple transformation like that, which is that if we start with an equation of this particular form, y equals f of x, and we transform it not by multiplying the right-hand side by a constant, but rather by adding a constant to the right-hand side, so that we end up with y equals f of x plus k, what happens geometrically? In other words, what does the graph of this new equation, this transformed equation, look like relative to the graph of the original equation? Well, this is very easy to see. So easy that you may be getting irritated with how slowly I am taking this. Because if I'm looking at y equals f of x plus k, I'm taking the y coordinate of each point and simply adding k to it, whatever k may be. So every point is literally being moved up the same amount. Unless, of course, k is negative, in which case every point is being moved down the same amount. It's just going to be a vertical shift by k units. So for example, if this is the graph of y equals f of x, then what would the graph of y equals f of x plus 4 look like? Well, of course, every point on that graph would move up by 4 units, because y, the outputs, are just going to be whatever they were before, plus 4 more. So in this case, that would look like this. What was it minus 2 moves up 4 units to 2. What was it 4 moves up 4 units to 8. What was it 0 moves up 4 units to 4, and so on and so forth. Or we could similarly shift the original graph down by 1 unit simply by subtracting 1 from the right-hand side. Okay, very easy. Now, I find most students are pretty comfortable with those two correspondences between algebraic transformations and geometric transformations. And it is indeed very easy so long as we are talking about vertical transformations. Here we had a vertical shift, a vertical stretch, vertical reflection, and the corresponding algebra was always just simply doing something to the right-hand side of the equation. Multiply it by k, add k to it. Very easy. Where people get messed up is when our transformations are, geometrically speaking, not vertical, but horizontal. Everything is very different. Everything comes out very nicely for the vertical ones because of this special form, y equals f of x, where the variable that tells us what's going on in a vertical sense, y, is isolated on one side of the equation. Well, if we have something like y is blah, 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 some function of x, we don't have x isolated on one side of the equation. So it's not as easy to see what happens. It's not that much harder, but it's not quite so obvious. So I want to dwell on that for a little bit. But first, let's wrap up all of this stuff that we've discovered in a table, because we're going to build a small table with 4 entries. And if you understand everything in that table, you will really understand how to deal with transformed sine waves more or less entirely. The 4 entries in my table are going to be algebraic transformation. And in the margins of my table, I'm going to have the corresponding geometry. The 2 particular transformations we're going to be interested in are a shift by k units and a stretch by a factor of k with a reflection if k is less than 0. Those are my 2 rows. My 2 columns, I'll be interested in whether we are doing these things vertically or horizontally. And everything that goes in our table pertains specifically to equations of the form y equals f of x. Very important. So not everything that goes in here will apply to all equations, just equations of this form. I do work out in chapter 6 how to do these things for any equation whatsoever, but we don't need that here in chapter 12 because we will only be working with equations of this form. So anyway, let's fill out what we know already, which is the first column. If we have y equals f of x, and we want to shift its graph vertically by k units, what do? We just add k to the right-hand side of our equation. That's what we discovered over here. Poof. If we have y equals f of x, and we want to stretch the graph vertically by a factor of k, possibly including a reflection, namely if k is less than 0, how do I do that algebraically? Well, we saw that before. We just multiply the right-hand side by k. That will give us a vertical stretch. Poof. So now we have to fill in the horizontal column. How are we going to do that? This takes a little more care, but it too is actually pretty easy if you think your way through it. And it's a good mental exercise to do this because it really gets you thinking about what is meant by the graph of an equation as the set of all points whose coordinates satisfy that equation. So let's think about horizontal shifts. I find that a lot of students remember what it is that you have to do algebraically to do a horizontal shift, but they don't quite understand why it is so. So hopefully I can get that point across here. So let's start with the geometry. Let's say I've got a graph of a function y equals f of x, and I shift it to the right by k units. Then I will end up with another graph that looks exactly the same. Of course, it's just moved down the road a little bit. The mystery, though, is what is the equation of this new graph? I know the equation of the original graph was y equals f of x, but as for this one, I have no idea. We are going to figure out an equation for this graph, because once I have an equation for it, then I should just be able to look at it and see what it is I have to do algebraically to my original equation to turn it into that thing. And then I will know how to fill in those cells in my table. Okay, so how do I find the equation of this graph? Well, we have to think about what it is that such an equation does. That equation, whatever it is, has the property that if I take any point on that shifted graph, like this one, which I'll just call xy because this is a variable point, it could represent any point on the graph. If I take any point and feed its coordinates into this mystery equation, I should get a true statement. That's what I'm looking for. I'm looking for an equation that has that property, that I could take the coordinates of any point on this graph, stick it in, and get a true statement. Okay, so let's see if we can figure out such an equation. Since this point, xy, lies on my shifted graph, I know that if I shot it backwards by k units, putting it on the original graph, then the coordinates of that point, that green point, would definitely satisfy this equation. It would give me a true statement. Well, that's kind of interesting, because I actually do know what the coordinates of this point are. Because the way I got this point was I started with xy, and I shifted it left by k units. So that means that the first coordinate would have to be x minus k. And the height of the point hasn't changed at all, so its y coordinate would still be y. So let me just write up in words what we have discovered. For any point xy on the shifted graph, we know that the point x minus ky lies on the original graph, whose equation, of course, is y equals f of x. So, well, what does that tell us? This point lies on the original graph, so the coordinates of that point satisfy that equation. Pop them in, x minus k for x and y for y, and we will get a true statement. So doing that, we know that what happens? Pop y in for y and we get y. Pop x minus k in for x and we get f of x minus k. This equation is a true statement. Hey, wait a second. Look what we have just discovered. For any point xy on the shifted graph, we know that y equals f of x minus k is a true statement. That's precisely the kind of thing we were looking for. We were looking for an equation that is satisfied by the coordinates of every point on the shifted graph. So this is indeed the equation we are looking for. Y equals f of x minus k. So let me import that right there. Now we know the equation of our shifted graph. Aha! That is progress. But is it going to help us fill in our missing column about horizontal transformations? We want to know what we have to do algebraically to an equation of the form y equals f of x to shift the graph horizontally by k units. Well, now it's very easy to see, because algebraically we're going from this equation to this equation. that is my transformation, my algebraic transformation. How do I make that happen? Well, I'm staring at it. All I have to do is everywhere I have an x, I substitute x minus k. So that's my algebraic move. To do a horizontal shift by k units, I'm going to substitute x minus k for x. And this is where students sometimes get confused because it is a substitution. We are popping x minus k in everywhere we see x. We're not just subtracting something or adding something to an entire side of an equation. We are making a rather more delicate substitution. Everywhere there's an x in the equation, we simply replace it by x minus k. In parentheses, of course, because we are thinking of the x minus k as one package. And the kind of place you would have been very likely to have seen this in the past in an algebra class would have been something like where you might start with everybody's favorite parabola, y equals x squared, and then shifted it to the right, maybe by 5 units, and then you might have been asked, what's the equation of that new parabola? Well, now we see. To shift it to the right by 5 units, we're just going to do this substitution. Everywhere there's an x, we are going to substitute x minus 5. And that is the equation of our shifted parabola. Of course, if we shift to the left, like say we shift to the left by 2 units, well, we could say that a horizontal shift to the left by 2 units is a horizontal shift by minus 2 units. That's how the negative would show up in there. So we would be substituting in x minus minus 2, or in other words, x plus 2 for x, for that leftward shift. So this guy would have the equation x equals the quantity x plus 2 squared. So, as I've said, you've almost certainly seen this sort of thing in that earlier context. And if you've read chapter 6, you've seen it in a still more general context. Now, the last cell of our table, horizontal stretches by a factor of k. To save time, I am not going to go through the argument. You should be able to figure it out yourself now. And I strongly encourage you to do just that. It's the same kind of argument. Think about what happens geometrically if I stretch this guy horizontally by a factor of k. Like if I stretch this by a factor of 2 horizontally, what would it look like? Well, all the x coordinates would be doubled. So something like this. Or if k was between 0 and 1, like a half, maybe it would look like that. Or if k was negative, it would be flipped as well. But no matter what it is, well, I guess I'm talking through the basics of it right here. No matter what it is, I'm not going to write everything out, but if we have any point xy on the stretched curve, that corresponds to a point on the original curve that would have coordinates what? Well, the y would still be the same. The height of the 2 points hasn't changed. But how did I get to this one? I multiplied the x coordinate by k. So I would have to divide by k to get back to that one. So this would be x over k. So without writing everything out, but just seeing if you can follow the argument quickly, that would mean that for any point xy on the stretched curve, the point x over ky lies on the original curve, so it satisfies the equation, the known equation of the original curve, which means if I pop those coordinates into that original equation, which would give me y equals f of not x, but x over k, that equation is satisfied by every point on that stretched curve, which means that that equation is going to be the equation of the stretched curve. So algebraically, how do I get from the equation of the original curve to the equation of the stretched curve? Well, of course, you can see it. You're staring at it. Everywhere I have an x in my original, I'm just going to substitute in x divided by k. And that is the algebraic transformation corresponding to a horizontal stretch by a factor of k. We are going to substitute x divided by k for x. Good. And the thing to remember is that the substitutions you use when you're doing these horizontal transformations are in some sense the reverse of what you might naively expect. To shift to the right by 5 units, you might naively expect that your substitution should involve x plus 5. It does not. It's going to involve x minus 5. To stretch by a factor of 32 horizontally, you might naively expect that your substitution would involve multiplying x by 32. That's not what you do. You have to divide x by 32 when you make that substitution. And it's easy to be put off by the lack of symmetry here. To do the vertical transformations, you just operate directly on the right-hand side. To do the horizontal transformations, you have to do these substitutions for x. That's all because of the lack of symmetry in the form of the equation that we are working with right here, where we have y isolated by itself, the vertical component isolated on one side of the equation, while x, the horizontal variable, can be smeared out all over the right-hand side. In fact, I will mention very quickly that there is a symmetry here if you look in a more general sense, because if I started with this y equals f of x, like so, when I add k to the right-hand side, that, of course, is equivalent to subtracting k from the left-hand side, which itself is equivalent to substituting y minus k for y. So we could have put in this cell, substitute y minus k for y, and then we would have perfect symmetry between the vertical and horizontal. And that would be very satisfying, but when we are dealing with functions of this special form, well, it's nicer just to say add k to the right-hand side, even at the risk of breaking the symmetry. My point is, there really is a symmetry there. It's just a few layers deeper than the way we're looking at it right now. Same thing holds right here, because if we have y equals f of x, and we multiply the right-hand side by k, well, that's equivalent to dividing the left-hand side by k, which is equivalent to substituting y over k for y. So we could have put in that cell, substitute y over k for y. It would be completely equivalent. And if we were working with equations that were not in this form, well, those substitutions for y would be exactly how we would carry out the vertical transformations. They actually hold in that form no matter what this equation looks like. It just so happens that when the equation is nice, we can rewrite the vertical ones in a simple form. Anyway, maybe that was more than you wanted to know. You don't need to know that for the stuff we're doing in this chapter, but it's all there in chapter 6 if you are interested. And now, our transformation table is complete, and it is time to move on to some concrete examples of how we can use it to transform sine waves. Let's sketch a graph of y equals 3 times cosine 4x minus 2. The trick is to recognize that the equation whose graph we want is just an algebraically transformed version of an equation whose graph we already know, namely y equals cosine x, whose graph, of course, looks like this. I'm just writing down one period. Of course, it continues on forever in both directions. So now the game is, if I can specify a sequence of algebraic moves, any of these 4 algebraic transformations in the body of my table, that will take me from y equals cosine x up to this thing, then all I have to do is think of the corresponding sequence of geometric transformations and apply those to the graph of y equals cosine x. So let's see, how do I get from cosine x to this thing? And I want to do it not all at once. I want a specific sequence of algebraic transformations. So let's see. The first move I might make is to start here in the interior. I'm going to turn cosine x into cosine 4x. And the way I do that, algebraically, is to substitute 4x for x. Of course, if I do that algebraic transformation on cosine x, it becomes y equals cosine of 4x. So far, so simple. What's the next algebraic move I should do to turn this thing into this? And maybe someone is thinking, oh, just do it all at once. You subtract 2 from the right-hand side and then multiply by 3. Careful, that won't do. We have to think about order of operations, because if we did that, we'd be starting with y equals cosine 4x, subtracting 2 from the right-hand side, and then multiplying the right-hand side by 3. There's no option in here to multiply just some little bit by 3. The only one of these moves that involves multiplication is multiply the right-hand side by k. The whole right-hand side, not just some little bit. And of course, if we did that here, we would end up with the wrong thing, because when we multiply that out, we would get 3 cosine 4x minus 6, which is not what we want. We're aiming at minus 2. So the order in which we do our sequence of operations is very important. So clearly what we want to do here is take this equation and multiply the right-hand side by 3, and then subtract 2. So I'll go ahead and write those two moves down. We'll multiply the right-hand side by 3, which turns this into y equals 3 times cosine 4x, and then we'll subtract 2 from the right-hand side, which will turn this into y equals 3 cosine 4x minus 2. And that is the target at which we were aiming. Good. So that means we have now specified a sequence of 1, 2, 3 algebraic transformations that takes plain old y equals cosine x to the equation that I want. Excellent. So now all we have to do is write down the corresponding sequence of geometric transformations and then apply them to the graph of cosine x. So substituting 4x for x, what does that do? Well, that's one of our horizontal transformations. And you might be a little confused here because you might think, hey, wait a second. I'm substituting 4x for x. X is being multiplied by 4 in my substitution. But this says division in the substitution. X over k, not x times k. But division is just another kind of multiplication. I think this will actually be a little clearer if instead of writing x over k, I were to rewrite that as 1 over k times x, which is of course the same thing as x divided by k. Substitute that for x. So the main thing to remember is that stretching by a factor of k horizontally, the factor that comes into our substitution is not k, but the reciprocal of k. So in this case, in this kind of a substitution, I'm stretching horizontally, not by a factor of 4, but by a factor of 1 over 4, right? Because the reciprocal of 1/4 is just plain old 4. So this algebraic substitution corresponds to a horizontal stretch, I'll just call it an H stretch, by a factor of 1/4. Let's go ahead and carry that geometric transformation out on our basic graph. When we do that, well, the basic shape doesn't change, but if we're stretching by a factor of 1/4, that means we're smushing it in horizontally so that the first period will be finished not in 2 pi, but in 2 pi divided by 4, which is pi over 2. So that I'd end up with something like that green stuff, where the whole period is packed into just pi over 2. But that, of course, would be very hard to read. There's no reason I have to keep the same scale as I move from sketch to sketch. So I will just change the labels on the horizontal axis. I know that the picture is still going to look something like this, but that the first period is going to be finished not at 2 pi, but at pi over 2. And I haven't changed so-called amplitude of the function. It still deviates from that line that it oscillates around, sometimes called the midline. It deviates from the midline by only as much as 1. If I wanted some more detail, of course, that minimum is going to be halfway between 0 and pi over 2. It's at pi over 4, and this point would be at pi over 8, which means this would be 3 pi over 8, but I don't need that kind of detail. This is just a rough sketch to remind me of what's going on. And that's it. That's the graph of cosine of 4x. But we still have a couple more transformations to do. We then took that equation and multiplied the right-hand side by 3 to get that. Well, what happens when you multiply the right-hand side by 3? It's a vertical stretch. And because it's vertical, we actually are stretching by a factor of 3. We don't have to deal with a reciprocal or anything like that. So I'll just say vertical stretch by a factor of 3. What does that do to this graph? Well, of course, it's going to make it so that it oscillates not between 1 and -1, but between 3 and -3. But again, I don't want to draw that giant thing, so I will put it over here and just change the vertical scale. And this is all just bookkeeping. My final nice graph will go down here. But anyway, we've made progress. Now we have the graph of 3 times cosine 4x. The last algebraic move is just to subtract 2 from the right-hand side. Well, we're operating on the right-hand side, so that means we're doing a vertical transformation. We're subtracting something, which is the same as adding a negative. So that's a vertical shift. We are shifting the graph down by 2 units. So that will take this graph, and instead of having a wave that oscillates around the horizontal axis as its midline, that midline is going to drop down 2 units to -2. And the function will still have the same amplitude of 3. It gets 3 units above the midline and 3 units below the midline. But instead of going 3 units up from 0 to 3 and 3 units down from 0 to -3, it's going to go 3 units up from -2 to 1 and 3 units down from -2 to -5. So it will look something like this. At least one period of it will. And of course, the period is pi over 2. So I better mark that on the horizontal axis as well. And having reached this point, which is a quick sketch of the graph of the function we are actually interested in, we can now write a more polished version down here. So let's do that. I've got my axes. They're labeled. I have my midline. I have the relevant values on the vertical axis. Now I will draw in one full period. Let me mark a few relevant points. The x-axis, period finishes at pi over 2. So that means this point, which corresponds to the bottom, must be half of that, which is pi over 4. And if I wanted to put it on, this is a relevant point too, where the graph crosses the midline. So if I come up to the axis, this is supposed to be halfway between those points. Well, half of pi over 4 is pi over 8. And the corresponding point over here would be, well, let's see. We're advancing in units of pi over 8. So pi over 8, 2 pi over 8, that would be 3 pi over 8. Now we have everything of interest on our picture of one period of the graph. I do need to put some more periods on there to remind viewers that this is indeed a periodic function. So I could just do those with a little less care, but some care. And note that this one, of course, that's going to be the end of the second period. The period is pi over 2, so that's going to be 2 of those, which is pi. And I could go on from there, and same story backwards. And that's it. We have a lovely graph. All the relevant information can be seen on it, except that my -5 is a little too small. We see the midline of -2. We see that we're going up 3 and down 3 from that. So we have an amplitude of 3. We see that the period is pi over 2. And what more could you want? So a bit of a pain, I grant you, but nothing difficult. One thing I will say is that once you get used to this sort of thing, you're probably not going to be putting separate sketches for each version of the function as you think about that sequence getting us from something known, cosine, to the unknown thing that we're working with. In practice, if I was doing this, I would probably just use one picture for my sketch. Now, mind you, when I say if I was doing this, I mean if I was doing this on my own, not demonstrating this to a student. If you're taking a test, you are trying to demonstrate something to your teacher. I'm going to be covering my tracks again and again on this picture. So it gives no indication of my thought process. That's what you have to demonstrate on a test. But I'm not just turning in the final product to you. I'm talking you through my thought process. Anyway, the graph of cosine x we know looks like this. When I do that substitution of 4x for x, I know it stretches it horizontally by a quarter. Well, again, rather than just drawing a compressed version, I'm just going to think, okay, well, if it compresses it horizontally by a quarter, instead of getting to 2 pi, it's going to get to a quarter of that, which is, of course, pi over 2. So I will literally just change the axis, or the label on the axis. So that corresponds to this. Then I'm multiplying the right-hand side by 3, which stretches it vertically by 3. What does that do? Oh, well, that just changes it so that instead of going from -1 to 1, it's going from -3 to 3. So this is a rough sketch of the graph of this one. And then I just have to push everything down by 2 when I subtract off that 2 from the right-hand side. And then I would probably just use this to create my final sketch. Now again, don't turn that in on your test because it gives no indication of where this thing came from. But when you're thinking about it on your own, after you've done this many times, that's probably the kind of thing you're going to do. And of course, you probably wouldn't write all this stuff out either if you're doing it on your own once you've gotten used to all of this stuff. But in the beginning, it's important to do that kind of thing so that you really understand what's going on, that you have this sequence of algebraic transformations that corresponds to a sequence of geometric transformations. Because that is a very important lesson, not just in this silly specific problem, but in thinking about coordinate geometry in general. If you look in a lot of trigonometry books, pre-calculus books, whatever, you'll see problems like this handled in what might seem like a more efficient way, where you just are told, well, this thing out front, that's the amplitude, and then you do something with this, and that will tell you the period, and this tells you how far it's shifted down, and that's all true, but it can turn into just like another thing to memorize, and of course, subsequently forget. And there's no value in that, whereas there's a lot of value of thinking about these transformations, because this holds far beyond this sort of silly problem. It holds for transformations of any sort of graph of a function, trigonometric or not. But let's do one more example with a couple of twists in it. So let's sketch a graph of y equals -2 times sine of the quantity 2x minus pi. This is a little different than the last one we did, plus 1. There are a couple of ways we might approach this. First of all, let's recognize that the -2 is not going to cause any problem. That's going to be a vertical stretch with a flip, a vertical flip. The plus 1 is not going to cause any problems. That is going to be a shift up, a vertical shift by 1. It's just this 2x minus pi that's a little strange. If it was just 2x, that would be easy. It would basically be like the problem we just did, but with a minus pi in there, that makes it a little trickier. So first let's do this in a kind of systematic way that will work for any equation that could arise that looks sort of like this. And then I'll show you a little trick that we could make this particular equation simpler. But let's start with a systematic way. The trick is to rewrite this stuff in the parentheses by factoring that 2 out of the expression in the parentheses. Why did I do that? I did that to expose this x minus pi over 2, because that looks like this substitution for a horizontal shift. Aha! Once we see that, it becomes much clearer what's going on. We have to take some care, though, with order of operations here. So let's start by thinking about a sequence of algebraic transformations that would take us from the basic underlying function here, which is y equals sine x, all the way to this function we're given. And once again, let's start with this stuff inside those parentheses, because that's going to be the tricky stuff. At the end, of course, once we can figure out how to get that, we'll just multiply the right-hand side by minus 2 and then add 1 to the right-hand side. But let's concentrate on that stuff. How are we going to do it? We can't do it all at once. We're going to need 2 steps. Should we first substitute x minus pi over 2 for x and then multiply by 2? No, that's not going to work, because we can't multiply just some portion of the equation by 2. If we're going to multiply something by 2, we can only multiply the entire right-hand side. That's not what we're doing there. So instead, we can get from x to this stuff by a sequence of 2 substitutions, but the order is very important. What we're going to do is first substitute 2x for x, so that we get y equals the sine of 2x, and then substitute x minus pi over 2 for x, which will give us the thing we wanted. Ah, very good. And do you see why I could not have done those substitutions in the reverse order? If I had tried to do so, I would have gone from y equals sine x, first making that substitution of x minus pi over 2 for x, and then substituting 2x for x, which would give me this sine of 2x minus pi over 2. Well, that is not what I am aiming at. In fact, what we want from our original is 2x minus pi, not 2x minus pi over 2. So the order is very important here, so please do write it out. If you write it out, then you will not get lost. Okay, and that's the hard part. Once we've got that, the rest is easy. We're going to multiply the right-hand side by minus 2, which just does that, and add 1 to the right-hand side, which takes us to our target. I'm sorry that is so small and cramped, but I have run out of room. Let's think about what happens here. We're starting with the familiar graph of sine x. As usual, I will just draw one period. When we substitute 2x for x, what is that? That's a horizontal stretch. It's a horizontal stretch by not 2, but by 1/2. So what happens in my graph? Instead of having a period of 2 pi, I will have a period of pi. It's still going between minus 1 and 1, of course. Now we're going to substitute x minus pi over 2 for x. What does that do? Ah, we haven't done one of those yet, so maybe I should write that down explicitly. That is going to be a shift to the right by pi over 2. So what's that going to look like? Well, to think about that, it's going to help to have a sense of some other significant points on this little preliminary sketch. The period is pi, so this thing must cross the horizontal axis at pi over 2. Oh, well, that makes it much clearer. This little thing is going to shift over and start right there. And that means, of course, it will continue on backwards like that. Okay, so maybe I'll put that picture over here. Okay, that's looking better. And let's see, the period hasn't changed. That's going to still be pi. So if I start a period at pi over 2, I add pi onto that. So half a pi and a full pi gives me 3/2 pi right there. And I could fill in, say, that's pi right there, and anything else I wanted, but that's good enough for now. This is just a preliminary sketch. Okay, from here, what do? We multiply the right-hand side by minus 2. What does that do? We are doing a vertical stretch by a factor of 2, and because of the negative, we are reflecting vertically. We're flipping over the horizontal axis. So the result will be, because of the stretch by 2, I'm not going between minus 1 and 1. We'll be going between minus 2 and 2. And everything is going to get flipped over. So it'll look like this. Okay, and then what's the last thing we do? We add 1 to the right-hand side. Of course, we know what that does. We're just moving everything up by 1 unit. So that is a upwards shift by 1. So rather than drawing another sketch here, I'm going to go ahead and put the final product down here. Everything is moving up by 1 unit. So instead of having the horizontal axis axis as our midline. That is going to be at y equals 1. The amplitude is 2. We're going up and down 2 units from our midline. So that will take me up to 3 at the top and minus 1 at the bottom. And now everything just moves up. So here's one full period, which we know is going to end at pi. That'll be pi over 2 right there. Peak will be at pi over 4. That trough will be at 3 pi over 4, and so on and so forth. Good. So that little trick we did in the beginning, taking that 2x minus pi, which looked mysterious, and factoring out that 2, that little trick is a nice one, and one you should definitely remember. And you can see why it's important, because it separates it out so that we get an x minus some constant, which is the sort of thing we use one of our substitutions for. You'll see things like this in the exercises. But I promised a while ago that there was another approach to this particular problem. This won't always work, but it will work on this one. Let me back up and start again and show you how a little preliminary thought can make our lives easier. I better keep the final product so that I can compare at the end. Okay, we want to graph this function, and we look at that 2x minus pi and we think, ugh, what am I going to do with that? Well, we've seen one solution, that systematic solution that would always work. But in this case, we might think, hey, wait a second, can't I come up with an identity for this kind of thing? I've got sine of something minus pi. That sounds like one of those on-the-fly identities. So let me just do some quick scratch work over here. Forget about the fact that it's sine of 2x minus pi. All I really care about is that it's the sine of something minus pi. So I might think, sine of theta minus pi. Is there a simple identity for that? Well, let's think about the unit circle. Maybe I can see something right away. Like if I have some typical angle theta, what's theta minus pi? What would that look like? Well, if that's theta, and then I'm subtracting pi off of theta, well, I'm doing a half turn from there in the reverse direction, which would take me over here. So sine of pi minus theta would be the y-coordinate of this point. Obviously, the y-coordinate of that point is equal but opposite to the y-coordinate of this point. And the y-coordinate of this point is just plain old sine of theta. Hey, so that means this is going to be minus sine theta. Oh, that's nice. Sine of anything minus theta is just minus sine of that anything. So in this case right here, I know that sine of 2x minus theta is going to be minus sine of 2x. Ah, but I mustn't forget the plus 1. And then that simplifies considerably because these two negatives cancel out, leaving me with 2 times sine 2x plus 1. And that's much nicer thing to graph than this original version. In fact, just for fun, let's see if we can do this one with very minimal notes as opposed to those with maximal notes, like the first example we did. Let's just think about what we would have to do here. This is based on y equals sine of x. We can get to this by the following sequence of operations. Substitute 2x for x, then multiply the right-hand side by 2, then add 1 to the right-hand side. So if I think about those, what am I going to get? I had my usual sine function, one period of which looks like that. Substitute 2x for x. That's a horizontal transformation. That's a stretch by a factor of not 2, but half. That means instead of taking it 2 pi, this period will only take pi, half as long. Then I doubled the right-hand side. That stretches it vertically by a factor of 2. So instead of going between minus 1 and 1, I am going to be going between 2 and minus 2. And then we add 1 to the right-hand side. That shifts everything up 1 unit. So that means instead of going between minus 2 and 2, I will actually be going between minus 1 and 3. Now I need to take a little care here because this is no longer the x-axis. So I will put that in, that my y. I will move that pi to a more sensible location. Maybe put a few extra important points on there. That's going to be pi over 2. Peak is at pi over 4. That trough is at 3 pi over 4. I can put on some extra periods just to demonstrate that I realize this is periodic. And hey, look, this is the same graph as what I had right down here. Starting at 1, starting at 1. Period of pi, period of pi. Amplitude of 2, amplitude of 2. And the moral of this particular story is that it is always nice to simplify when you can, but realizing that you could even do that depends on having a feel for the sine function. Not just knowing it as something you've memorized, a list of facts, but being able to see an expression like that and think, hey, sine of something minus pi. That sure sounds like the kind of thing I could read off of the unit circle. And then doing that, and then making the appropriate change. Nobody in the world memorizes that sine of theta minus pi is minus sine of theta. It's true, but it's the kind of thing you just bash out when you need it, or when it seems strategically useful, as it did right here. Okay, let's do one last example. This one going the opposite direction. Instead of a problem where I give you a function and ask you to graph it, let's start with a graph of a transformed sine wave, or a sinusoidal function, if you want to use the fancy lingo, and I will ask you to find a function whose graph looks like this. And since I'm getting afraid of running into traffic jams here, and I assume you already have this transformation table written down in your notes, if not firmly lodged in your memory already from Chapter 6, I'm going to get rid of it. Plenty of room for our solution. Okay, how are we going to find a function whose graph looks like this? First, we recognize that this is clearly a sinusoidal function, a transformed sine wave. It looks like the sine wave. It starts, well, at least at the midline, if not at 0, goes through a period, well, it's not of 2 pi, but of 14, and it bobbles up and down with an amplitude of, what is that? 14. That's the distance between the midline and its extreme values. So I'm going to make another one of these little charts where I start with something familiar, y equals sine of x, and more specifically, I want to think about its graph. That's really my starting point, because what I want to do now is think about how I could transform that graph with geometric transformations to turn this graph into my target graph using only the geometric transformations in my dearly departed transformation table, stretches and shifts. So let's see, what am I going to do? Ultimately, I'm going to need to take my sine wave, stretch it out horizontally, so that instead of having a period of 2 pi, 6 1/4 roughly, it will have a period of 14. I'm going to need to stretch it vertically, so that instead of having an amplitude of 1, it will have that amplitude of 14. Why did I put 2 14s in here? Well, such is life. 2 14s it is. And I will need to shift it up, so that instead of having a midline of the horizontal axis, the midline will be here at y equals 22. Let's start by working on the period. Clearly, as I said before, we need to stretch this thing out. So the first thing we are going to need to do is do a horizontal stretch. But the question is, by what factor? Well, by whatever factor will take me from 2 pi to 14. Well, then I have to ask, what do I multiply by to turn 2 pi into 14? Well, I want to get rid of the 2 pi, so of course I'm going to have 2 pi downstairs, and I want a 14, so I'm going to put 14 upstairs. If I multiply 2 pi by 14 over 2 pi, of course I get 14. That'll do the job. And this point, which was at 2 pi, will now be at 14. But I'm going to reduce that to 7 over pi. Okay, so once I do that, my graph will look a little better from my perspective. It will be still bobbling between -1 and 1, but now with the appropriate period of 14. Now what? Well, of course, as we said, we need to change the amplitude from 1 to yet another 14 by sheer coincidence, since 14 is the distance from 22 to 36, or 22 to 8. So let's do a vertical stretch by plain old 14. That will turn my graph into something that looks like this. 14's as far as the eye can see. But I'm not quite done. We need one more transformation. We need to shift this sucker up, not, thank God, by 14, but by 22 units, which will put my midline up at y equals 22, and the range of the function between 8 and 36, which is exactly what I wanted. Great! So I've got a sequence of 3 geometric transformations that will take me from the very familiar sine wave to this sinusoidal function I'm aiming at. Now I just have to think about the corresponding algebraic transformations. Well, a horizontal stretch by 7 over pi, that's a substitution for x, and everything gets reversed. We're not substituting 7 over pi x for x. We are taking the reciprocal of that thing. So we are substituting pi over 7x for x. A vertical stretch by 14. That's easy. We just take the right-hand side and multiply by 14. A shift up by 22. That's easy too. We just take the right-hand side and add 22. So now, these are the 3 algebraic transformations we have to do in that order to our original function sine of x. That first one, the substitution, turns it into y equals sine of pi over 7x. This next one turns it into y equals 14 times sine of pi over 7x. And the last one, adding 22 to the right-hand side, turns it into y equals 14 sine pi over 7x plus 22, and that is it. If you were to graph this thing on your favorite graphing program, you would see something very much like that. And this sort of thing is not just an idle exercise. Any kind of periodic behavior, like in the book, I give an example of the population of a certain species of fish in a certain area, but it could be whatever. It could be drawn from biology, economics, physics, you name it. Anything where something is going through some cycle and we're modeling it. We might think first, okay, what does this thing look like? Something like this, where we start at a certain value, go through certain values, and then keep repeating it, so on and so forth. Now, how do I come up with a function to capture that? Well, it's the kind of process we did right here. And that, I think, is a good place to end this video, which brings Chapter 12 to a close. I'll see you next time in Chapter 13. Fare thee well. Adios.